Right now, as you are watching this, Earth is being hit by solar energy arriving from angles that should not be possible. Not from one direction, not from a single coronal mass ejection traveling the standard path from the Sun to our planet. From multiple directions, simultaneously, with geomagnetic disturbances being recorded at monitoring stations in Canada, across Europe, and as far south as Australia, within the same observation window. Space weather scientists tracking the real-time data are describing the current configuration as one of the more unusual they have documented in this solar cycle. And once you understand what is actually happening, not the simplified version, but the real mechanism, you will understand why this is not a story about a single solar storm. It is a story about what happens when the entire space environment between the Sun and Earth becomes unstable at the same time. The alerts started arriving at geomagnetic observatories in rapid succession. Canada's Natural Resources Monitoring Network flagged elevated disturbance indices across its northern stations first, which is not unusual. Canada sits directly under the auroral oval, the ring of maximum geomagnetic activity that surrounds the magnetic pole, and it is typically the first to register incoming solar energy. What was unusual was the timing of what came next. Rather than the disturbance propagating in the expected pattern, hitting the polar regions first, then gradually expanding equatorward as the event intensified, monitoring stations in Central Europe began recording their own independent disturbance signature before the Canadian event had resolved. And then, as scientists were processing the European data, the stations in Australia reported anomalous readings of their own. 3 geographically separated regions, 3 partially overlapping but distinct disturbance signatures, 1 observation window. To understand why this configuration is unusual enough to be worth this level of attention, you need to understand how a standard geomagnetic storm works and why multiple simultaneous disturbances arriving from different directions breaks that standard picture. A typical solar storm follows a sequence that space weather forecasters have become quite good at tracking. A region of the Sun's surface becomes magnetically unstable. That instability releases energy in one or both of 2 forms: a solar flare, which is an intense burst of electromagnetic radiation that travels to Earth at the speed of light and arrives in approximately 8 minutes, and a coronal mass ejection, which is an enormous cloud of magnetized plasma that travels considerably slower and typically arrives at Earth between 1 and 3 days after launch. When the CME arrives, it interacts with Earth's magnetosphere, the magnetic bubble that surrounds and protects the planet. And if the magnetic field orientation of the CME is aligned in the right way relative to Earth's field, it causes a geomagnetic storm. That storm manifests as a global disturbance in Earth's magnetic field, most intense at high latitudes and potentially severe enough at high activity levels to affect power grids, satellite operations, GPS accuracy, and radio communications. That is the standard scenario. Single source, single propagation direction, predictable sequence of effects. What has been observed in this event does not fit that template cleanly. The data shows characteristics consistent with at least 2 distinct solar sources contributing to the current geomagnetic environment, and the timing and geometry of the disturbances detected across Canada, Europe, and Australia suggest that the magnetosphere is responding to arrivals that are not simply different phases of the same event. They appear to be genuinely separate, with different magnetic field orientations, different arrival angles, and different effects on the specific regions of the magnetosphere they are interacting with. The Sun, at this point in solar cycle 25, is producing exactly the kind of complex multi-source activity that makes this scenario possible. Solar cycle 25 has significantly exceeded the predictions that solar physicists made for it. Those predictions, based on historical cycle patterns and models of the solar dynamo, projected a relatively modest cycle, less active than the preceding cycle, with a moderate solar maximum. Instead, solar cycle 25 has been running approximately 40% above the predicted activity level. The solar maximum, which is the peak of the sunspot cycle where activity is highest, has produced event rates that some forecasters were not expecting to see. And crucially, the current phase of the cycle has seen the development of multiple active regions, areas of intense magnetic complexity on the Sun's surface, distributed across the solar disk at the same time. When multiple active regions exist simultaneously, the probability of overlapping or interacting CME events arriving at Earth increases substantially. The specific mechanism that can produce the multi-directional effect being observed involves something called solar energetic particle events, and the way that different CMEs, launched at different times and from different locations on the Sun's surface, can interact with each other during transit through interplanetary space. When 2 or more CMEs are en route to Earth simultaneously, they do not necessarily travel as independent structures. The first CME modifies the interplanetary medium it is traveling through, compressing the solar wind ahead of it and creating a region of altered magnetic field and plasma density. When a subsequent CME travels through this modified environment, it can be accelerated, deflected, or merged with the preceding structure in ways that alter both its trajectory and its magnetic field orientation. The compound structure that arrives at Earth is not simply the sum of the individual CMEs, it has properties that neither CME would have had alone, and the effects it produces on the magnetosphere can be more complex and longer lasting than a single discrete event. What this means for the current observations is that what looks like simultaneous arrivals from multiple directions may be, at least in part, the result of a single complex structure that has been distorted during transit in ways that cause different portions of it to interact with different regions of Earth's magnetosphere at slightly different times and angles. The magnetosphere is not a simple uniform shield. It has a day side, facing the sun, where the field is compressed by solar wind pressure. It has a night side, stretched into a long magnetotail by the solar wind flowing past. It has polar cusps, regions near the magnetic poles where the field lines converge and where solar particles have direct access to the upper atmosphere. And it has a vast array of boundary layers and current systems that respond differently to incoming solar energy, depending on the orientation of that energy's magnetic field. A complex incoming solar structure can simultaneously perturb several of these regions in ways that produce geographically separated surface disturbances, which may be at least part of what the Canadian, European, and Australian data is reflecting. The Australian readings deserve specific attention because they are the most scientifically significant element of this event. Geomagnetic disturbances in Australia, at mid-latitudes well south of the auroral oval, require considerably more energy input than the disturbances that routinely affect Canada. For a storm to be detected at Australian latitudes, the Geomagnetic Activity Index, the KP index, which runs from 0 to 9, with 9 being the most severe, needs to reach levels that push the visible aurora and associated disturbances well below their normal polar boundaries. The Halloween storms of 2003 produced aurora visible from Australia. The May 2024 storms, which were the most powerful in approximately 2 decades, also produced low-latitude aurora visible from Australia and caused radar systems to detect aurora from regions that rarely see such activity. The current readings from Australian stations are not at that level, but they are elevated enough to be notable, and they appear to be connected to a component of the current disturbance that is distinct from the higher latitude Canadian event, rather than simply the southern extension of the same disturbance propagating equatorward in the standard way. The radio communication effects being observed are one of the cleaner diagnostics of what is actually happening in the upper atmosphere right now. High-frequency radio communication, the kind used by aviation, maritime operators, amateur radio operators, and some military and emergency communication systems, depends on the ionosphere, the layer of the atmosphere that is ionized by solar radiation, and that reflects certain radio frequencies back to Earth, allowing communication over long distances. When a solar flare hits, the immediate surge of X-ray and extreme ultraviolet radiation dramatically increases ionization on the sunlit side of Earth, absorbing rather than reflecting HF radio signals and causing blackouts that can last from minutes to hours. When the CME arrives subsequently, the associated geomagnetic storm modifies the ionosphere in different and longer-lasting ways, creating irregular structures in the ionospheric plasma that degrade radio propagation unpredictably. What operators are currently reporting across multiple regions is consistent with both of these effects occurring in overlapping fashion. The signature of multiple solar impulsive events affecting the ionosphere in rapid succession, without the normal recovery window between them. The GPS implications of this kind of complex, extended disturbance are significant and deserve to be understood clearly. Modern GPS accuracy depends on extremely precise timing signals transmitted by satellites and received by ground-based receivers. The signal passes through the ionosphere on the way from satellite to receiver, and the ionosphere introduces a delay in the signal that is proportional to the electron density along the path. Under normal conditions, this delay can be modeled and corrected for, allowing GPS receivers to achieve the accuracy that users expect. During geomagnetic storms, the ionosphere becomes irregular and turbulent in ways that make the delay spatially and temporally variable in patterns that are difficult to model. The result is degraded GPS accuracy, and in severe cases, complete loss of position lock for receivers that rely on single-frequency signals. Aviation GPS approaches, precision agriculture systems, surveying operations, and the timing signals that synchronize telecommunications networks all depend on GPS functioning within normal accuracy specifications. During the current event, accuracy degradations, consistent with ionospheric disturbance, have been reported across multiple regions, though the severity has so far remained within manageable bounds for most users. The aurora activity associated with this event has been producing displays visible far outside the normally active auroral zones, and the reports coming in from observers across multiple continents confirm the global scale of the current disturbance. Aurora at mid-latitudes is driven by the equatorward expansion of the auroral oval as geomagnetic activity intensifies, and the visibility reports from this event are consistent with activity levels that push that boundary well into regions where most observers have never seen a natural aurora display. The physics of the aurora itself is worth understanding in this context, because it is not simply a pretty light show. It is the visible manifestation of energy being deposited into the upper atmosphere by charged particles that have followed the magnetic field lines down from space. The intensity and geographic extent of the aurora is a direct indicator of how much energy the magnetosphere is currently processing, and the current displays are indicating a significant energy input rate. The power grid implications of a geomagnetic storm of this complexity and duration are something that grid operators take extremely seriously, and the steps being taken in real time by power system operators in Canada and Northern Europe reflect the level of concern that the current event is generating. The mechanism by which geomagnetic storms affect power grids involves something called geomagnetically induced currents, GICs. When the magnetic field at Earth's surface changes rapidly, which it does during a geomagnetic storm, it induces electrical currents in any long conducting structure at the surface. Pipelines, railway tracks, and most significantly, power transmission lines all act as antennas for these induced currents. High voltage transformers at the ends of long transmission lines are particularly vulnerable because the GICs that flow through them during storms can bias the magnetic cores of the transformers in ways that cause them to overheat, produce harmonic distortions in the power signal, and, in severe cases, suffer irreversible damage. A high voltage transformer is not a component that can be quickly replaced. Lead times for custom large power transformers can be measured in years. The 1989 Quebec geomagnetic storm, which resulted from a major CME impact, collapsed the Hydro-Quebec power grid in 90 seconds and left 6 million people without power for up to 9 hours. The damage to transformers in that event took considerable time to repair. Grid operators in vulnerable regions monitor the real-time magnetic field data continuously during events like the current one, and are prepared to implement protective measures, including controlled load shedding and protective relay adjustments to reduce the risk of transformer damage. What space weather scientists are watching most closely right now is what happens in the next 12 to 24 hours. The current multi-source event has produced a magnetospheric configuration that is, by the assessment of the researchers analyzing it, not yet at its most disturbed state. The interplanetary magnetic field, the magnetic field carried by the solar wind, has been fluctuating in orientation in ways that have produced periods of stronger and weaker magnetospheric compression, and forecasters are watching for a sustained southward orientation of the interplanetary field, which is the condition that most efficiently couples solar wind energy into the magnetosphere and drives the most intense geomagnetic storms. If a sustained southward field develops in association with the remaining portions of the incoming solar structure, activity levels could intensify further before they begin to subside. The real-time monitoring infrastructure that allows scientists to watch this unfold is itself worth appreciating for what it represents. The DS-Govier spacecraft, operated by NOAA, sits at the Lagrange point between Earth and Sun, approximately 1.5 million kilometers upstream of Earth in the solar wind. It measures the solar wind speed, density, and magnetic field orientation, and transmits that data in near real time to forecasters on the ground, giving approximately 15 to 45 minutes of warning before those solar wind conditions reach Earth's magnetosphere. That window is narrow, but it is enough for grid operators to take protective action and for satellite operators to put sensitive instruments into safe mode. Before spacecraft like DS-Govier existed, the first indication of a major solar storm's arrival was the storm itself. The fact that we now have even a short warning window is the result of decades of investment in space weather infrastructure that most people never think about until it is needed. Solar cycle 25 still has activity ahead of it. The solar maximum was recent, and the declining phase of a solar cycle, which is where we are now entering, does not mean the storm risk disappears. Some of the most severe historical geomagnetic storms have occurred on the declining side of the solar cycle, when large magnetically complex active regions can still develop and launch powerful CMEs. The current event is a demonstration that the risk environment remains elevated. The multi-source, multi-directional nature of what is being observed right now, the Canadian alerts, the European signatures, the Australian readings, all within the same window, is the kind of event that space weather researchers use as a case study for understanding how the worst-case scenarios can develop and what the real-time data looks like in the hours before conditions reach their most severe. This is a developing situation. The instruments are running. The data is updating. And if you want to be here when the next alert arrives, whether that is a further intensification of the current event or the next significant storm in the weeks ahead, subscribe to this channel now and turn on notifications. Drop a comment telling us where you are and whether you have seen Aurora or experienced any communication disruptions from this event. The geographic spread of reports from viewers is itself valuable information about how widely this disturbance is being felt. This is the kind of science that is happening right now, in real time, above every one of our heads. The satellite operators who are most exposed to the current event are not the large, well-resourced government agencies that maintain their own space weather monitoring and engineering teams. They are the operators of the thousands of smaller commercial satellites that have been placed into low Earth orbit as part of the recent explosion in commercial space activity. Low Earth orbit, which extends from roughly 200 to 2,000 kilometers altitude, sits largely within or just above the upper fringes of Earth's atmosphere. During geomagnetic storms, the upper atmosphere heats up and expands, a phenomenon called thermospheric expansion, because the energy deposited by the storm drives increased atmospheric heating at high altitudes. This expansion increases the density of the atmosphere at the altitudes where LEO satellites operate, and the increased atmospheric drag that results causes satellites to lose altitude faster than their normal decay rate. For satellites with propulsion systems, this means consuming more fuel than planned to maintain their orbits. For satellites without propulsion systems, including many of the small cube satellites launched by universities and smaller commercial operators, it means shortened operational lifetimes and, in the most severe cases, rapid unplanned re-entry. The February 2022 event, when SpaceX launched 49 Starlink satellites directly into a geomagnetic storm that then dramatically intensified, and the resulting thermospheric expansion caused 38 of those satellites to re-enter the atmosphere before they could raise their orbits to operational altitude, was the clearest recent demonstration of how consequential this particular storm effect can be. SpaceX lost nearly 80% of a single launch batch at a cost of tens of millions of dollars because the geomagnetic conditions between launch and orbit raising changed faster than the satellite's propulsion systems could compensate for. That event involved a single storm pulse. The current multi-source event, with its complex timing and potentially extended duration, presents a similar or greater challenge for any satellites currently in low, unraised orbits. The ionospheric effects of a complex multi-source storm like the current one also affect systems that most people would not immediately associate with space weather. Modern agricultural operations increasingly rely on GPS-based precision farming equipment, planters, sprayers, and harvesters guided by RTK GPS systems that deliver centimeter-level accuracy. During geomagnetic storm conditions, the ionospheric irregularities that degrade standard GPS accuracy are even more damaging to the differential corrections that RTK systems rely on, because the ionospheric delay corrections transmitted from ground reference stations become invalid when the ionosphere between the reference station and the rover receiver is behaving inconsistently. Farmers operating precision equipment during geomagnetic disturbances can find their systems functioning poorly or refusing to operate at all, which, during critical planting or harvesting windows, can have direct economic consequences that most discussions of space weather impacts never reach. Emergency services communications are another category of real-world impact that unfolds below the level of public visibility during these events. The HF radio systems that serve as backup communication infrastructure for many emergency management agencies, the systems that are supposed to work when cellular networks and internet communications fail during disasters, are precisely the systems most affected by the ionospheric disturbances that accompany geomagnetic storms. The irony is not lost on the emergency management community. The events most likely to cause infrastructure damage and communication failures are also the events that degrade the backup communication systems designed to manage that damage. This is one of the reasons that space weather awareness has become a more prominent part of emergency preparedness planning in recent years, and why organizations like FEMA and its international equivalents have developed specific protocols for operations during solar storm conditions. The scientific value of a multi-source event like the current one extends well beyond the immediate practical concerns. Each complex solar storm is an experiment that the sun runs on the magnetospheric system, and the data collected during such events is what drives the refinement of the models that forecasters use to predict the next one. The specific configuration of the current event, multiple source regions, interacting CME structures, complex magnetospheric response, is exactly the kind of scenario that existing forecast models handle least well. The single CME scenario has been modeled extensively, and forecasters can predict its effects with reasonable skill. The multi-CME interaction scenario remains one of the more poorly constrained aspects of operational space weather forecasting, precisely because these events are complex, relatively infrequent, and produce effects that depend on the specific geometry of the interaction in ways that are difficult to generalize. The data being collected right now by DSCOVR, by the AC spacecraft, also sitting in the solar wind upstream of Earth, by the network of ground-based magnetometers, by ionospheric monitoring stations, by the GPS networks whose receiver data can be inverted to map ionospheric electron density in near real time. All of this data will be archived and will feed into research that improves the next generation of forecasting models. The scientists who study space weather think about every major event not only as a hazard to be managed, but as an observational opportunity. The more severe and complex the event, the more it stresses the system in ways that reveal dynamics that routine activity does not. And understanding those dynamics is what eventually makes the forecasts better. The warnings earlier and the impacts smaller. There is also a deeper scientific thread running through events like this one that connects to questions much larger than operational space weather forecasting. The interaction between the solar wind and Earth's magnetosphere is one of the fundamental plasma physics laboratories accessible to human science. The processes that occur at the magnetopause, the boundary where the solar wind meets the magnetosphere, involve magnetic reconnection, a process where magnetic field lines from two different regions break and reconnect in new configurations, releasing enormous amounts of energy in the process. Magnetic reconnection is not unique to Earth's magnetosphere. It occurs in the solar corona. It drives solar flares. It is believed to be important in astrophysical jets, in the dynamics of neutron stars, and in a range of other extreme environments. Understanding how it works at Earth, where it can be observed with an array of instruments that no other astrophysical environment permits, has implications for plasma physics broadly. Every major geomagnetic storm is an opportunity to observe magnetic reconnection operating at a scale and with an intensity that laboratory experiments cannot replicate, and that most astrophysical environments are too distant to resolve. The current event will pass. Within days, the geomagnetic activity will subside, the ionosphere will recover, and the space weather alert levels will step back down through the scale toward quiet conditions. The Aurora will retreat to its normal polar home. GPS accuracy will return to standard specifications. Radio propagation will normalize. Power grid operators will stand down from elevated alert status. The immediate event will be over, but the conditions that produced it will not have changed. Solar cycle 25 is active, more active than predicted, and the population of active regions on the sun's surface that can produce complex multi-CME events will remain present throughout the remainder of this cycle. The next event of this kind is not a question of whether. It is a question of when, and whether the infrastructure that civilization increasingly depends on, the satellites, the power grids, the navigation systems, the communication networks, will be in a better state of preparation when it arrives than it was for this one. Space weather is not a niche interest for radio hobbyists and aurora photographers. It is a physical environment that the infrastructure of the modern world depends on operating within. And when that environment becomes disturbed in the way it is right now, the effects propagate through systems that billions of people rely on without knowing that space weather exists. The goal of a channel like this one is to make that connection visible, to give you the framework to understand what the monitoring data means, what the alerts represent, and why the readings coming in from Canada, Europe, and Australia right now are worth paying attention to. Not because there's a reason to be alarmed beyond what the data supports, but because the data itself, when you understand it, is one of the more remarkable, real-time windows into the physics of the solar system that exists. Subscribe if this is the lens you want to use to watch the sun. Turn on notifications so you are here when the next alert arrives. And tell us in the comments where you're watching from and what you are seeing, because your location is data, and data is how we understand what is happening right now, above every one of our heads, at scales that make everything else feel very small. What is unfolding right now is also a test, not just for the infrastructure and the forecast models, but for the broader public understanding of where risk in the modern world actually comes from. Most people carry a mental model of technological risk that is firmly terrestrial. Cyber attacks, equipment failures, supply chain disruptions, extreme weather. The idea that a ball of plasma launched from the surface of the sun 1 to 3 days ago is currently stressing the power grid in Canada, interfering with aviation communications across Europe, and producing geomagnetic readings in Australia that are elevated enough to be flagged as scientifically notable. That idea sits outside the intuitive risk landscape for most people, and yet it is precisely accurate. It is what is happening right now. The Carrington event of 1859 remains the benchmark for what a truly severe solar storm can produce. On September 1st and 2nd of that year, a solar flare, an associated CME of exceptional power, struck Earth. The telegraph systems of North America and Europe, the most sophisticated electrical infrastructure of the era, were overwhelmed by the induced currents. Operators reported sparks flying from their equipment. Some systems continued to operate even after being disconnected from their power supplies, driven entirely by the geomagnetically induced currents flowing through the telegraph lines. The aurora was visible from tropical latitudes. In the Rocky Mountains, the glow was bright enough that gold miners woke up believing it was morning and began preparing breakfast. The storm lasted approximately 2 days. The Carrington event occurred when the most sophisticated electrical infrastructure on Earth was a network of telegraph wires. If an equivalent event occurred today, the infrastructure exposed to the induced currents would include hundreds of thousands of kilometers of high-voltage transmission lines, fiber optic repeater systems, undersea communication cables, natural gas pipelines, and the timing and navigation satellites that modern infrastructure increasingly depends on for synchronization and positioning. The estimated economic impact of a Carrington-class event in the modern era has been modeled by multiple research groups. The figures they produce, ranging from hundreds of billions to trillions of dollars, with recovery times measured in years rather than days, are large enough that they sit in the category of civilizational risk rather than operational disruption. A 2013 Lloyd's of London report on the topic used the phrase potential for long-duration, widespread power outages that would affect a significant fraction of the population of the affected regions for extended periods. The current event is not a Carrington-class event. The monitoring data makes that clear. The disturbances being recorded across Canada, Europe, and Australia, while notable and worth tracking, are within the range of what the existing infrastructure is designed to manage. But the current event is happening on a sun that is more active than predicted, in a solar cycle that has exceeded forecasts by a significant margin, during a period when the population of large active regions on the solar disk is elevated. The Carrington event was produced by a single exceptional active region that scientists of the era did not have the instruments to detect in advance. Today's monitoring infrastructure would detect the precursor flares and provide warning. Whether the warning would be sufficient to protect the most vulnerable infrastructure from a Carrington-scale CME is a question that space weather scientists and engineers are still working to answer. And the honest answer is that for the most severe conceivable events, the current warning and protection systems may not be adequate. This is not a reason for alarm, it is a reason for awareness. The difference between a population that understands the basic physics of what the sun can do and a population that does not is the difference between a risk that is managed and a risk that arrives without context. The alerts from Canada, Europe, and Australia right now are the monitoring system doing exactly what it was designed to do: detecting elevated activity, characterizing the disturbance, communicating it to the operators and scientists who need to act on it. The fact that you are watching a video that explains what those alerts mean and where they fit in the larger picture of solar activity and Earth-Sun interaction is itself a small part of how a society builds the collective understanding that eventually gets translated into better preparation, better infrastructure, and better outcomes when the more severe events arrive. The storm overhead is real. The science behind it is knowable. And the channel that explains it in real time, every time the sun does something that matters. That channel is this one. Subscribe, turn on the bell, and stay with us as this event develops. The data from this event will be archived. The researchers will analyze it, the models will be refined. And the next time a complex multi-source storm develops, the next time alerts arrive simultaneously from widely separated monitoring networks, the next time the magnetosphere is stressed from multiple angles at once, the forecast will be a little sharper, the warning a little earlier, the response a little better calibrated. That is how the science works. That is how, over decades, the understanding of space weather has moved from curiosity to operational necessity. And events like the one unfolding right now, unusual enough to demand attention, complex enough to push the models, global enough in its footprint to produce readings from Canada to Europe to Australia simultaneously, these are the events that drive that progress most efficiently. The sun, in its extraordinary and occasionally inconvenient way, is teaching us something. The question is always whether we are paying attention when the lesson arrives.